it's, excuse me, sorry. It's around time for us to get started. Feels like we're slightly late today, so some people are probably out at the thing, which is fine. So the first thing I want to talk about is an announcement I put on Brightspace yesterday. I'm not sure how many people saw it. That is kind of how I communicate with the class at large, is through the Brightspace announcements. Yesterday was the last day to drop the class, and your tests are not graded yet. And I feel like there may be some people who are waiting on getting the test back before deciding about the drop, which is totally legitimate. So to alleviate any concerns you might have, I made two decisions. Decision number one was that if you do better on the final exam than you did on this test one, I'll move the weight of this test to the final exam. So for example, if you don't do so hot on this test, you get 75 on the final exam, it'll be like you got 75 on this test. So the weight can come off this test as long as you improve. So if it's not to your benefit, of course, I won't change it, but if it's to your benefit, I will. I'm gonna apply that to the class at large. You don't have to email me separately to ask or anything. I'll look at the grades at the end and do that myself. The second thing is when you get your test back, if you do wanna drop the course, if you come talk to me right away, I'll work with you to avoid those academic penalties for dropping after the drop date. So if you really want to drop, but you just didn't because you don't know about the test, come talk to me and I'll see what I can do. I hope you'll stay with the course and be very successful. However, I don't want to limit you in kind of whatever choices are best for you. Any questions there? Okay, super. So last day, we finished off with our fourth property of the conductor, which said that the charge density was the largest, where objects have a steep curve, which means that they're pointy. So I thought we would start today with an application of that. The first one I have is a video. I did not take this video. Anybody used to live in Ontario or a place to get thunderstorms? Some people are kind of familiar with thunderstorms. This is a thunderstorm in Ontario in Toronto. I don't know if they speak much. So this is lightning hitting the CN tower. So the old thing is lightning never strikes twice. Everybody heard this thing before? Sort of an old statement. Clearly that's not true. This night it struck the CN tower 40 times basically in a row. So lightning certainly can and does strike twice. But this goes to our application of things that are pointy, having big electric fields. The CN tower has a lightning rod on the top. It's a big, tall spike of metal. It, because it's a spike, has a very high charge density, which means it has a high electric field. It attracts the lightning to itself because the field is so high. There's a big force and the lightning is attracted to that. Ultimately, that's a very good thing, right? You don't want that lightning to hit everywhere else. You want it to hit a spot where it can be channeled down out into the ground and dissipate safely. So people who live in Ontario, frequently, I won't say always because nobody does everything always, but frequently will have lightning rods on their house because it keeps it safe. When you were kids, if you went out in a thunderstorm, your parents tell you to do anything, be careful of anything. First of all, probably come home out of it. Second of all,
stick to low ground.
Stay on low ground.
Don't go under a tree.
Don't go under a tree. If you're out in a lightning storm, you don't want to be the big, tall, pointy thing, right? Because people have lots of electric fields. If you're the one standing up in a field, you're the one getting hit by the lightning because you're the big, tall, pointy thing, right? So if there's lightning strikes nearby, come on and lie flat on the ground. So something like that. So don't be the tall thing. What else? Yeah, don't hold your umbrella up in a storm, right? Because it would be attracted to the umbrella, the pointy thing. The other thing I have about potential, and this feels like a good place to bring it in. I'm gonna need to change the light in here though. This isn't like the best thing ever. So this is called a Wimhurst machine. I have asked my friend John if he'll fix the Van de Graaff for us. He's gonna have a look at it. I gave him a pair of pantyhose and he thinks he can fix it. But this is kind of not another bad application. What happens is I'm gonna turn the wheel. This has some little brushes that are gonna make contact with the metal bits of the wheel. It's gonna draw electrons and charge out of the air. It gets stored, the charge, in these two jars here. They're called Leyden jars. One is positive, one is negative. The charge is going to transfer to these spheres right here. So there's going to be a potential difference between the two spheres. Can you see it? Probably everybody can hear it. I might be able to get it go a little bit more. See the screen going fine? That's because of this. So what's happening is the two spheres are getting piles of equal and opposite charge. So there's a huge potential difference between them. There's a potential difference across a space. That means there's a very large electric field. Typically, charge doesn't travel through an insulator, which air is. Typically, air is an insulator. But when the electric field gets so high, so this amount of charge over that small distance, air actually breaks down and becomes a conductor. So the air becomes a conductor between those 2 points, and that happens when your electric field gets to about 3 million volts per meter. So you could look at this little separation. It's about 1 centimeter. We know the electric field is about 3,000 volts per meter. You could calculate the potential difference between those 2 points. So that's our point of dielectric breakdown. That's a mini version of lightning. With lightning, the cloud gets one large charge. The Earth has another large charge. When the charges get so big, we get that breakdown, and the spark, the lightning, travels from the cloud to the ground. Okay, so there's that. Any questions before we keep going?
How dangerous would it have been if someone were to stick their finger in between those two nodes right there?
No, that's fine. That won't kill you.
Okay.
No. It'll probably hurt. It'd be like a static electricity shock when you touch a doorknob. It's the same deal, right? When you scuff your feet across the carpet and you touch the doorknob, that's what happened just there. Yeah. So that sort of potential difference, that's not the kind that kills you. The one that kills you is from the high current and the changing potentials. Okay, so the next thing we're going to look at and talk about is a slightly new way to visualize electric potential and to draw a relationship between electric potential and electric fields. So a new way to look at those and talk about them together. Anybody recognize what this is? Yeah, that's Mount Fuji. Which is cool. Anybody ever been to Mount Fuji? I haven't, but it is definitely on the list. So down here, people who have done a geography class maybe recognize what these are, contour maps. Is that ringing a bell from geography class for some people? So Mount Fuji is pretty tall. It's got a height of about 3,700 meters. So that's the top is 37 meters high. When we draw a contour map, what we do is we draw a line everywhere on that hill where it has the same height. So for example, everywhere on this red line, it's 3,000 meters above sea level. Everywhere on this line, it's 2,500 meters above. Those are contour maps in geography. This one is a 3D version. This one is a 2D projection of that map. These are really useful in geography because they give a lot of information about the topology of the land. Something you might notice is places where the lines are very close together. See if we can find a spot. For example, right here. Where they're very close together, it shows that the height separation changes over a small distance. That makes the hill steep. Places where they're spread out, maybe over here, the height changes over a big distance. That means it's kind of shallow. When I take my bike around St. John's, sometimes I look at a contour map. I'm looking for level ground, not hilly ground. Not lots of it in St. John's, but it is what I look for. So we're going to do the same sort of thing with electric potential. We're going to draw graphs of electric potential, how it changes in space, and that's going to give us an idea of electric fields. So the stuff we do next will help you on at least a couple of your assignment problems that are posted. So when we talk about lines with equal potential, so those are going to be like our contour maps, but instead of equal height, it's all going to have equal potential. Those are called equipotential lines. So those are lines along which the electric potential, or V, or potential difference, is always a constant value. We might want to remember here something we said about electric potential, and this was in one of the posted videos. If electric potential is constant, that means delta V is equal to 0. It means it has to be perpendicular to the electric field lines. Potential only changes when you move parallel to the field. It doesn't change when you move perpendicular. Okay, so there's something to think about. And when we draw our lines, we always space them evenly in potential. So 10 volts apart, 100 volts apart, 1,000 volts apart. So when we draw our maps, that's what they're going to look like. So let's look at the relationship between electric field and electric potential. So what we thought about when we looked at our capacitor was that the electric potential was E, the electric field, times the distance from the negative plate. So over on our capacitor, our S value is an axis that goes from the negative plate towards the positive. We say at the negative plate, that's S equals 0. At the positive plate, we're at the maximum separation between the plates. Normally we label that D, like S equals D. So there's our axis. In this problem, I'm saying that the electric field is 100,000 newtons per coulomb, or volts per meter. So for these different values of distance relative to the negative plate, I could go ahead and calculate the potentials. So it's just the field times the distance. So for example, everywhere where my distance from the plate is 0, my potential V is equal to my electric field E times my value of S, 0, equals 0. So everywhere that S equals 0 has a potential equal to 0. That leads me to draw my first line. Notice it doesn't matter where we are vertically. All that matters is that we're 0 millimeters from that plate. So this line is V equals 0. 0.25 millimeters across. My potential is going to be my electric field times 0.25 times 10 to the minus 3 to put it in meters. Gives me a potential of 25 volts. So everywhere that we're 1/4 of a millimeter away from that plate, the potential is 25 volts. And then 1/2 millimeter apart, we're at 50 volts. 0.75 millimeters, we're at 75 volts. 1 millimeter, the full distance over, we're at 100 volts. You can draw all of those lines. 50 volts, 75 volts, and 100 volts. So all of these orange lines that I just drew, those are the equipotential lines. And mostly when I say equipotential lines, I'm just going to abbreviate EPL, so when I write it down, so I don't have to write that out a million times. Okay, questions? We are starting with the simplest case in between the plates of a capacitor where the electric field is constant. We will get more complicated very soon. So some things that we notice about our relationship between the electric field lines and the equipotential lines. First of all, our equipotential lines are all vertical, and the electric field lines are all horizontal. Those two things are perpendicular. Okay, so that's something that we have. So the equipotential lines are perpendicular to the electric field lines. Okay, a little bit of shorthand there, but hopefully that makes sense. So all of our equipotential lines are perpendicular to our electric field lines, which is what we said when we said that they're lines where the potential is constant. When we move perpendicular to the electric field, we don't get a change in potential. And that comes from the scalar product nature of potential and field. We also notice that our electric field, which points from the positive to the negative, goes from 100 volts to 0 volts. So our electric field lines points towards low potential. And that's something we discussed when we analyzed that equation, and here we can see it visually. All of our lines, we chose them to be evenly spaced in potential. That statement is always going to be true because that's how we draw these lines. For this particular example, we see that they're also evenly spaced in distance. That's because our electric field is constant. So you might start to wonder what would happen if the electric field wasn't constant. What would that mean about the spacing of the lines? And we'll get at that next. And then last, and this is more of a heads up of what will be coming, we often use all of these concepts with our electric potential energy, which is charge times the potential. We also use it with the fact that work is minus the change in potential energy. And we use it with conservation of energy. B final is the initial plus work done by non-conservative forces. Okay, so that's just a tip to remember that these problems tend to go together. All good? So let's go from a constant electric field to a changing electric field. And the example we'll look at is a point charge, because we do lots of point charges. So let's say we'd like to look at the electric potential around a 10 nanocoulomb charge. For a symbol, I'm going to call my charge Q. We know that the electric field is not constant, so what does that mean about the potential? There's kind of two ways we could visualize it. Number one, we could just draw a graph. So we could make a graph. We know that potential V is equal to K times charge divided by distance. So if we put V on our vertical, distance from the charge on our horizontal. If R is small, V is big, falls off as 1 over R. And as R gets big, V gets small. So that would be a graph of potential as a function of distance. That helps us know how the potential changes with distance from that charge. Another way we do it, and this tends to be really helpful, would be to draw the equipotential lines around that charge. So that's another way we can look at it. So let's ask, how are we going to draw these equipotential lines? That was kind of straightforward to the capacitor, but maybe it gets a little bit more complicated with a spherical charge. So what we need are lines that are evenly spaced in potential. So how do we know where to draw them? So what we'll do is let's pick a set of potentials that we want, and let's find the distance. Knowing the distance will let us know where to draw them. So our last example, we picked our distances and calculated our V's. This time we're going to work backwards. Let's pick all of our potentials. So these are the lines we want to draw, but where are we going to draw them? Well, we know V equals KQ over R. I know V because I chose them in my table. I know Q because it's 10 nanocoulombs. R is the thing I'd like to find. So R, the distance from my charge, is going to be K times Q divided by V. If we think about this in particular, what does this mean? So R is the distance from my charge Q. If I'm a constant distance from my charge, it means my lines are going to be circles or spheres in 3 dimensions. So a constant distance around a point charge is going to give me spheres. So if my potential is 2500 volts, that is going to give me a distance of 36 millimeters. I could go ahead and draw that line. So from my charge here, my plus Q here, 36 millimeters away. Will be a circle with a radius of 36 millimeters. So this is my 2500 volts. If I pick my potential to be 5000 volts, then my distance away is 18 millimeters. So I'm choosing to space my potentials by 2,500 volts. You could pick any value you want, it just has to be even amounts apart. My next potential would be 7,500 volts. That gives me a spacing of 12 millimeters. This one is 7,500 volts. My next one will be 10,000. That happens at 9 millimeters. That's in here. And then my last one I'm going to draw 12,500 is at 7.2 millimeters. I don't think I can squeeze it in, so I'll just draw an arrow labeling those. So those are my equipotential lines around a point charge. We notice here that they're evenly spaced in potential, but they are not evenly spaced in distance. So let's think about my electric field. We know what the electric field looks like around a point charge. And the electric field around a point charge is radially outwards. Outwards because we have a positive charge. So let's draw those lines on top of this map. So here are my electric field lines. So let's see what we can recognize about these relationships. First of all, we notice that the electric field lines are radially out. My equipotential lines are spheres. Those two things are perpendicular. So we have that same behavior. My equipotential lines are perpendicular to my electric field lines. Okay, same behavior there. That'll be the same behavior everywhere. That's always going to be true. Electric field lines point towards lower potential. It goes from 12,500 to 2,500. We also notice that our electric field, remember we had said when we drew electric field lines, electric fields are strong where the electric field lines are close. So the electric field lines are strong in close to our charge. That's where the equipotential lines are the closest together. So just like on geography contour maps, when the lines are close together, the hill is steep. Here, where our equipotential lines are close together, the electric field is big. There's our relationship. So E is strongest, where our equipotential lines are closest. So the density of those lines gives you the strength of the field. I'm sorry, but could I just ask if you've got your phones out to lay them down on your desk? I don't care if you're checking Facebook or whatever, just don't have it held up. And here we might put in our relationship between field and potential. The component of your electric field is the change in potential with respect to distance. And that's something we did a couple of examples of in last class. So are we all good to hear? A tool I really like to use for these equipotential maps and electric field maps is that PhET simulation. So let's switch to that and do a little bit there before we move on from this chapter. Just try and get everybody caught up on the notes first. So let's do this on our PhET simulation, and let's see that we're going to get basically the same answers. Oh my goodness. So if you want to use this, and I would recommend you do a little bit of work with this simulation, especially as you're going through your homework and stuff. So if you Google PhET, P-H-E-T, electric fields, this will be your first hit, launch to simulation, and it'll take you to this page. So what I'm going to do is take a positive point charge and just put it in place. So these lines are showing me the electric fields, and we did this before when we were drawing electric field lines. Our arrows are pointing away from the charge because it's positive, and they're radially outwards. The intensity of the color shows the strength of the electric fields. We can draw the equipotential lines here. So this little guy here, that's over here in this box, that's a sensor that measures the electric potential. So I'm going to move this till I get a potential in place. I think I'll go in as far as 20 volts. So I'm going to space them by 5. So 19.98, that's close enough for me. Turn on the values. So there's a 20 volt line. I'll go out a little further. I'll get a 15 volt line. Then I'll get 10 volts. And then 5 volts. Okay, that's about as good as I can do quickly. So this exactly matches what we drew from thinking about what we had. So the equipotential lines are circles, or in 3 dimensions they're spheres. They're perpendicular to the electric field lines. We can also use a sensor to measure the electric field. So if I put my sensor in close to my charge, my field is huge and points away. As I move further and further away where the lines are spaced out, my electric field gets smaller and smaller and smaller. Right? It never quite gets to 0 until we hit infinity, but it does decrease as we move away. So let's go through using this PhET simulation to figure out some stuff. I've got one posted that I'm going to leave for homework, and I'm going to go through one in class. For people who kind of want a picture of that, I am going to post one in with the class slides for today. Okay, so what we're going to go through in the next little bit is a configuration of charge where we've got 4 charges, 2 positive, 2 negative. They're going to be on a square, on the corners of a square. And what we're going to do is use the simulation. We're going to use it to draw the electric field lines, the equipotential lines. We're going to find the field and the potential at the center of the square. I'm probably not going to do the rest of it because it's just kind of too much and what's the point. And then we'll do kind of some work and energy analysis as well. So that's where we're going to go with this. So let's switch over to that simulation. And if you want to do this along with me, sort of on your phones or your iPads, like no problem, just open up PhET, P-H-E-T, electric fields, and you can do this as I do this. So I'm going to get rid of this charge. It gets rid of all of that stuff. I'm going to put my 4 charges in place. So I've got a positive here, and positive here, negative here, and a negative here. So this simulation is showing us our electric field lines. So if we wish, we could go ahead and draw those. So I'll switch back to the dot cam. The last time I taught this class, I was in a room that had 2 screens. It was great. I could keep the simulation open and move back and forth to the paper. But we don't have that here, so that's too bad. So for our electric field lines, and this is something we could have done in the last chapter when we studied this, we know that we go out of the positive into the negative. So our first lines we can draw like this. If charges have equal magnitudes and they have equal numbers of lines, so every time I go out of a positive, I'm going to go into a negative. Because we have so much symmetry in the problem, all of my lines are going to have a symmetry to them as well. Barring my drawing skills, of course. And my electric field lines are never allowed to cross. Okay, something like that. That's not the best drawing ever, but hopefully you're getting the idea. So there's my electric field lines. Those were kind of easy to draw based on the principles that we did in our last chapter. If you looked at this, you could get some ideas on how to draw the equipotential lines. We know that they have to be evenly spaced in potential, and we know they have to be perpendicular to the field. Some people who are probably really good with spatial awareness and drawing could maybe look at these lines and draw those equipotential lines. For the rest of us, it could be a little bit harder. So let's switch over to our simulation, and let's see if that can help us draw the equipotential lines. Okay, so back to the simulation. Let's find our equipotential lines. So I'm going to do my first one at 0. You might guess that the 0 line would be sort of right in between everything. If that's what you guessed, you would be correct. Draw. So there's my first equipotential line. My next one I'm going to go for is negative 10 volts. Plus 10 and minus 10. There's my plus 10. My minus 10 is over here, sort of doing the same thing on the negative side. And then, because I don't want to be here all day, I'll also do the 20s and the minus 20s, and then we'll stop. This sort of a task is kind of fair game for a homework assignment, but I wouldn't expect you to use a simulation in the middle of a test. But this is certainly something you could use while you're doing your studying. So this lets us see what the equipotential lines are. Let's change over to our drawing and put that on paper. So our equipotential lines, we had a 0 line right down through the center, 0 volts. Had kind of a figure 8 around the positives. That was our 10 volt line. And we had a couple of circles, squish circles around the positives. Those were our 20 volt lines. And likewise over on the negative side, everything was really symmetric. Minus 10 volts. And a couple of squish circles for our minus 20 volts. Hopefully this example is going to help you out with one we have in the assignment where we have 3 charges and one of these maps of equipotential lines. So that's what this is intended to help you out with. Any questions here? So the next part of our example, find the field and the potential at the center of the square. So we want to find the field and the potential right here. Let's do that with our simulation first. Then we'll sort of go back to our OG way of adding up the vectors and the potentials. And then we'll find a new way to figure out electric field when we know something about the potentials. So first I'll use my simulation. So right here at the center of the square, that was where our 0 potential line was. That means our potential at the center of the square is 0. And for our electric field, I'm going to put my electric field sensor in, and I'm going to put that right at the center of the square. Right at the center of the square, the electric field is 12.7 volts per meter to the right. So that's using our simulation to get our answers. Let's write those down. So at the center, B equals 0 volts. E equals 12.7 volts per meter, or newtons per coulomb, to the right, which I'll call I. So that's one way to solve it. Any questions here? Okay, next let's kind of quickly review the vector addition method. So for our vector addition method, I just preloaded a slide where I drew in my charges. we'd like to find the electric field right at the center of the square. So I'm gonna try and do this pretty quickly because we've done the examples before. And we probably don't need to kind of do all of the nitty-gritty details. So if we want to find the electric field at a certain place, we have 4 charges, 1, 2, 3, and 4. That means we're going to have 4 contributions to the electric field, which means we should draw 4 electric field vectors. The electric field at point P due to charge 1 is positive, so the electric field points away. Here's my electric field E1. For charge 2, that's a negative charge. The electric field points towards that charge. So my E2 will start at P, go in towards my charge, E2. Charge 3, that's a positive, so the electric field points away. Here's my E3. For charge 4, that's a negative. My electric field points towards E4. Everybody okay with those 4 vectors? So let's see if we can take advantage of some symmetry here. 2 of the vectors point right and up, 2 of the vectors point right and down. They're all equal magnitude charges. They're all the same distance from the charges. That tells us that the magnitudes of all those fields will be the same.
So you just have to calculate the cos.
Yeah. Oh, putting 2 2's, E3 and E4. They all have the same magnitude. That's due to symmetry. They're all at the same angle. That angle is 45 degrees. This angle is 45 degrees. Because we're at the center of a square and the angle between the diagonal and the horizontal is going to be 45 degrees. So that tells us that the sum of the y components equals 0 due to symmetry. And then to your point, the sum of the x components is going to be 4 times the x component of any one of them. The x component of any one of them is going to be the magnitude times the cosine of the angle. To find the magnitude of the electric field, we'll do k times q divided by r squared. Cosine of 45 degrees is root 2 over 2. Just one of those numbers that has stuck with me. Same for sine 45. So we know k, we know q, we want r squared. R is our distance from our charge to our point. So that's half the length of the diagonal of the square. So r is going to be the square root of L over 2 squared plus L over 2 squared equals L divided by root 2. Okay, so that's how we find that value. So we've got 4 times k times q. R squared is going to be L squared over 2 times root 2 over 2. Our q value was 1 nanocoulomb. That gives us an electric field magnitude of 12.6 newtons per coulomb. And as a vector, it would be 12.6 newtons per coulomb to the right. If we wanted to draw it, we could put that in there as well. Okay, I know I did that really fast. Any questions? Anybody get lost in the middle?
Right, so the y pieces were canceled, but they're all going towards positive x.
Exactly. So up and right, down and right, down and right. So
This
the,
is just like one of the questions on the assignment, and I could not figure it
Yeah?
out. So
well, maybe this will help.
Yep.
Okay, good. Okay, so there's our electric field at the center. On our simulation, we found 12.7 volts per meter. I get 12.6 newtons per coulomb. That's basically the same answer. Okay, so the simulation matches the math, so that is good. Let's do the electric potential as well. For our electric potential, that one's gonna be even faster because our potentials are scalars. So the distance between any charge and the point is that same value of R. My electric potential at any one point is the sum of all the individual potentials. We're not drawing vectors here because they're not vectors, they're just numbers. So my potential due to charge 1 is K times the charge Q divided by R. My potential due to charge 2 is K times the charge, which is minus Q divided by R. Plus my potential due to charge 3, K times Q over R, plus my potential due to charge 4, K times minus Q over R equals 0. Okay, so the total potential is 0 because we have that symmetry about where the plus and minus charges are placed. Are we still good? So those are two of kind of the original ways we calculated field and potential. Now let's bring in the new way of finding field from an equipotential map. So I'm going to go back to the simulation briefly. And what I want to do on the simulation is just put in a couple of new equipotential lines. So I'm going to put in a couple of 5-volt lines. There's one. And another one. So we could put in some more lines if we wanted to. By rights, now that I've put in the 5s, I should put in the 15s and the 25s. But I'm not going to do that because it'll take forever. So here we have to remember that electric field is the change in potential divided by the change in distance. And this is definitely one of your assignment problems. To do our change in potential, what we have to do is look at where we want the field. We'd like to find it right in the center. So to find a change, it means a change between 2 points. So we need to pick 2 points, one on the left of our point and one on the right. So let's pick a point here on our 5.2 equipotential line and a point right here on our 5.1. Delta V is going to be the difference between those two. And we can use our scale, which is down here on the bottom, to find the space between those 2 points. Okay, so that'll give us delta V. We'll measure delta S, and we can divide those to get our electric field. So what I did was I preloaded that slide, that simulation on a picture, just so that you could have some notes to put in your notes. Does that make it any easier to see? I didn't realize how dark that was going to be. Okay, so this is the map we were just looking at. Here's our zero potential line. This one is at 5.1 volts, and this one is at minus 5.1 volts. So 5.1 volts minus 5.1 volts. So my 2 points I was going to pick are going to be evenly spaced on my 2 equipotential lines. So point A and point B. My potential at A equals 5.1 volts. My potential at B minus 5.1 volts. My distance between the two, on the grid on the simulation, each little square corresponds to 10 centimeters. That's what the scale tells us. So the distance between those 2 points, delta S, is about 8.1 lines. You'd have to open up the simulation, turn on the grid, then you can count them for yourself. Or you can look at the slides after I get them posted. And it's 10 centimeters per line, according to the scale. So that distance is 0.81 meters. So the size of our electric field is the size of the change in potential divided by the separation. So 5.1 volts minus a minus 5.1 volts divided by 0.81 meters gives us 12.6 volts per meter. Okay, so the electric field we found 3 different ways, all matched, so that's a good thing. So we have 3 different ways to find electric electric field. Change in potential over distance, or use our sensor, or do our vector calculation. They're all gonna give us the right answer. Okay, any questions? All right, so the last little bit, let's do a work and energy example. And I am gonna post these notes afterwards. I wanna get through the first example before we quit, so I don't wanna come back to it next day. So if we released a proton at rest at point A, what will be its speed when it gets to point B? And how much work was done as it moved? So this is a very typical kind of question. So our proton is here at point A. We know a proton is a positive charge, so it will feel a force equals charge times electric field. That means it's going to follow the electric field line. That's the motion our proton is gonna take. So it's gonna follow along those lines until it gets to point B. If we wanna figure out how fast it's going, we can apply conservation of energy. Final energy is initial energy, plus work done by non-conservative forces. There's no friction slowing down our proton, so the work done is 0. Our final energy is final kinetic plus final potential. Initial energy is initial kinetic plus initial potential. The only thing that's 0 right off the bat is we release it from rest, so our initial kinetic is equal to 0. So now for our final, that's where we're at point B. So our kinetic at B plus our potential at B is our potential at A. Kinetic energy at B is a half times the mass of the proton times the speed at B squared, plus my potential at point B. My potential is my charge. Oh, sorry, I said potential and I meant to say potential energy. So kinetic energy plus potential energy. Potential energy is the charge of the proton times the potential at point B. Those two things added up is going to give us the charge of the proton times the potential at point A. Okay, so we're just applying conservation of energy where we know values from our equipotential map. So the speed of our proton is going to be the charge of the proton times the potential at A, subtract the potential at B. I'm taking QVB over to this side. I'm going to divide both sides by a half times the mass of the proton. I'll take the square root to get our speed. So my potential at A is 20.8 volts. My potential at B is minus 20 volts. Mass of a proton, 1.67 times 10 to the minus 27 kilograms. Charge of a proton is plus of that fundamental charge. Put that through the calculator and we get 8.84 meters per second. So it actually doesn't get moving that fast. So this is a low change in potential for a proton to move around. It also doesn't go all that far. How much work was done? For our work is minus the change in potential energy, which is minus the charge of the proton times the change in potential. So minus the charge of the proton times the potential at B, subtract the potential at A. Put all that through the calculator and we get plus 6.53 times 10 to the minus 18 joules. That the work is positive tells us that the force and the path are in the same direction, so the proton moves along the path naturally. The very last tiny example I wanted to do, I think I'm just going to post this for you guys to look at yourself, is what if we move an electron along the 0 volt line? So that's the one that I'll leave and post for you to look at. It's going to follow this exact same process, but it's going to be a lot easier because the potential stays the same. So we'll see that when we move along an equipotential line, the speed doesn't change and the work done is 0. Okay, that takes us almost up to time's up. So we'll quit there and then we'll start the capacitor chapter on Friday.